Okay, the information given to you describes that a leg, or legs, refers to the side or sides of a right triangle that form a right angle with another part of the right triangle. In the figure below, which line segment is a leg? So it says that the leg or legs form a right angle. So there are actually two lines that it takes to form a right angle. So there are two possible legs on this particular shape. One of them is XZ, which is answer choice B. One of them is YZ or ZY, doesn't really matter which order you put it in. Which means two of these, actually both of them, XZ and ZY, are both legs. So, when we're talking about legs, show me with your fingers, how many legs can there be in a right triangle? Maximum.
2.
And how many legs does there absolutely have to be? Right, I see that you showed me 2 for both of those answers. If it's a right triangle, it has to have a right angle, which means it has to have 2 legs. All right triangles have 2 legs. Now let's be clear here. If a triangle is not a right triangle, can it have legs?
No.
No, it cannot. Because if it's not a right triangle, that means it doesn't have a right angle. All right. Let's move over here. Another geometry term. Please show me answer for do now problem number 4. The last and final do now problem. Excellent. Let's talk about this word really quickly. It says in geometry the hypotenuse. Let's break that down. Hypotenuse. Everybody say it. Hypotenuse. Hypotenuse. One more time. Hypotenuse. Hypotenuse. Uh-oh, I heard somebody who didn't say it. Or scratch that. I didn't hear somebody say that. Everybody, one more time. Hypotenuse. Hypotenuse. All right. A hypotenuse, it says, is the longest side of a right triangle. So again, once again, we're talking about right triangles and right triangles only. It's the longest side of the triangle that does not form the right angle. So there's only one possibility here. This is the only line segment that does not form part of the right triangle, or part of the right angle over here, which means it's the only thing that is not a leg. So if it's not a leg, it is a hypotenuse. How many hypotenuses can a right triangle have? 2. The answer is 1. If a right triangle has to have 2 legs, that means only one particular side is left to be the hypotenuse. So what we have learned here in our do now is 2 things. Number 1, all right triangles have 2 legs and 1 hypotenuse. And the 2 legs are the ones that make the right angle. All right, let's move on to our classwork. So our aim for today is to use some of this information that we have just learned, and we're going to be talking about right triangles. Specifically, we are going to be able to find the length of a right triangles. It says a right triangles, which means that ols is a possessive ols. A right triangle's hypotenuse, the hypotenuse that belongs to a right triangle. We're going to find the length of a right triangle's hypotenuse using something called Pythagorean Theorem. We'll work on that word here in a second. Pythagorean Theorem. 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 We're going to find the length of a right triangle's hypotenuse using Pythagorean Theorem. Now, Pythagorean Theorem. Pythagorean Theorem is a math concept that was named for a Greek dude who lived 2,500 years ago in Greece. That makes sense. He's Greek. He lived in Greece. He was a philosopher. He was a well-known philosopher in his time. And to this day, we all say the name Pythagoras at some point in our lives because we learn this concept. So here we are 2,500 years later, and every person who has finished middle school math knows the name Pythagoras. That's pretty awesome. Pythagoras didn't do anything that was incredibly remarkable as far as I'm concerned, because we're going to do the exact same thing in class here today. All Pythagoras did was recognize a pattern with right triangles. So we're going to do exactly what Pythagoras did 2,500 years ago and prove to everybody that everybody in this room deserves to have their name remembered 2,500 years from now, just like Pythagoras did. I'll remember your names 2,500 years from now. Possibly. All right. So here we have a right triangle. And what Pythagoras first did is he said, well, okay, I recognize the lengths of these sides, 3 and 4. And for whatever reason, he started looking at squares related to the sides of these triangles. So he would draw a square. This is a 3 by 3 square to fit the length of this side. And he said that the area of that square was 9. Not interesting yet. And he'd come over here and say, all right, well, this side is 4, so I'm going to draw a square. Think about a square. That is 4 by 4. And the area of that square is 16. And then he's looking at this other side. Now, this other side, it's going to be much more difficult to draw a square for this and know the area and the length of that square because it actually comes across our grid lines. So what Pythagoras would have done was he would have taken a grid paper, much like you have in front of you, and he would have cut out a square and lined it up to find out how long that side is going to be. So you are going to do the exact same thing right now with the grid paper that is in front of you and the scissors that are in front of you. You are going to cut out a square and line it up just where I have drawn my square. That is the correct size for the length of this hypotenuse. So at this point, we don't know the length of this hypotenuse, but by golly, you're going to figure it out. All right? So please take 2 minutes, and I expect to see a square cut out for everybody, ready to paste on their paper. What I should see on everybody's paper right now is that you have a square lined up that looks like this. And the square should be 5 by 5. What is the area of a 5 by 5 squared? 25. So it should be 25. At this point, you might start recognizing something that is interesting. Coming up with an idea or a hypothesis about maybe what Pythagoras happened to notice about these squares and these triangles. I want you to go ahead and keep that in your mind. And we're going to try and do the same thing with our second triangle over here. So we're going to do the same thing with our second triangle, and hopefully that will kind of allow you to test your hypothesis. So you're going to be starting by creating these squares for the 2 legs that you can on the grid, and then finding the areas of those squares, and then cutting out another square to find the length of the hypotenuse. So you're going to be hopefully looking for something that looks exactly the same as your work over here for this triangle. Once you have done that, you should be able to answer this question that asks you to recognize a relationship between the lengths of the sides of the triangle, or at least the sizes of the squares. Should be looking for a pattern. All right. We have this on our paper. We figured out that this one was a 10 by 10 square. Gave us an area of 100. Somebody with a raised hand. What pattern did you recognize? Monia.
If you add 36, wait, yeah, you're looking at that one. If you add 36 plus 64, you get 100.
Okay, so she's saying if we add this 36 and this 64, we get the 100 for the other square. let's make sure that that worked for our other triangle as well. We add our 9 and our 16 and we get 25. This seems to make sense. So let's just be a little bit more clear this time when we describe that. What these numbers are and what they stand for on our paper. Alright, so the 36 is we'll call it the size or the square. How about that? The square of one of the legs. I liked how Jaime threw that in there. If we add the squares of the legs, we get the square of the hypotenuse. So, just thinking about what that means, again, just going back to our visual representation, if we add the square for this leg and the square for this leg, that gave us the square for the hypotenuse. Now we're going to do what Pythagoras did. This is the pattern that he noticed. These were the words that he was thinking in his head, and then he said to himself, well, I want to start putting this into math terms. So he would start by making a pseudo math equation. Remember we talked about pseudo math earlier in the year? Pseudo math is kind of equations that half use words and half use equation symbols and things like that. So the first thing that we said was that we add the squares of the two legs. Well, let's start by writing the square of one leg. How can I use pseudo math to kind of mathematically represent the square of a leg? How can I mathematically represent the square of a leg? Adolfo. Alright, so he's saying leg 1 squared, and if we're going to add that to the other leg, we need to add leg 2 squared. So we have taken the length of our leg, 6, squared it, plus the length of our leg, 8, squared it. And when we add those two things together, what would we get? We get 100 in this particular problem, but more generally, what did we call that particular part of our work? The hypotenuse, but was it the hypotenuse's length or was it the hypotenuse's square? Yeah, it was the hypotenuse's square, so we want to look at it here. So we know that we can square the length of leg 1, add that to the square of the length of leg 2, and that's going to give us the square of the hypotenuse. We just proved that visually. So, if we go back and again look at our example one more time, what we're saying here is we have our length was 6, we squared that, that gave us 36. Our length was 8, we squared that, we got 64. That told us that our hypotenuse, the square of our hypotenuse was going to be 100, which helped us figure out that the length was actually 10, or 10 squared was 100. So what Pythagoras then did, he took his pseudo-math equation, he said, let's make this really general. To make it really general, he wrote this very basic problem. He says, I have a triangle that has 3 sides. It is a right triangle. I'm just going to call one side A, one side B, and the hypotenuse I'm going to call C. So his 2 legs are A and B, and his hypotenuse is C. Using the pseudo-math equation that we just used, how can I replace it and use these variables? Esteban.
A plus B equals C.
A plus B equals C. Now, that would suggest to me that if I add the lengths of the sides of the triangle, I'm going to get the right thing. Is that right? What do you need to add there, Esteban? Square where?
Square on A, B, and C.
Yeah, so A squared plus B squared equals C squared. It's the squares that add up to get the square of the hypotenuse. That's all Pythagoras did. Every one of you in this room just went through the process that Pythagoras did 2,500 years ago that has us still talking about him today. So, if you had just been 2,500 years earlier, we'd be talking about the Cranian theory or the Bibianoian theory. Okay? Or the Rhodian theory. Okay? Psalm is pushing us ahead to look at some problems. She's saying, well, I see that this is a right triangle, which means if it is a right triangle, I know the relationship between the sides are a squared plus b squared equals c squared. The first thing that Psalm wants to do when she's looking at this problem is make sure that she's correctly identified what A, B, and C are. A and B are always the legs. The legs make a right angle. So I find my right angle here, which means I know that these two are my legs, so I have to label them both A and B. One of the most common mistakes in problems like these is to incorrectly label A, B, and C. If you plug things into the equation wrong, you're obviously not going to get a correct answer. So we're looking for our unknown side over here, which is C. So we start plugging in 6 squared plus 8 squared is equal to C squared. I don't know C squared. I'm trying to figure out what C squared is. In fact, I don't even want to figure out what C squared is. I want this length. I want actual C. So I can continue to work on this. Simplifying it a little bit further. And simplifying it even a little bit further. I get that C squared is equal to 100. Now, again, I want to know the length of the hypotenuse, not the size of its square. So right now, we know the size of its square is 100. At this point, we need to finish solving this equation for C. We talked way back in Unit 2, and then again in Unit 7, about the inverse operation of squaring something. Somebody with a raised hand who remembers this. What is the inverse operation for squaring something? Triana. Squaring is not quite multiplying. It's a very specific type of multiplying, which means we have a very specific thing that we do in the inverse. Amanda?
You find the root of the...
Perfect. We find the square root. So what that does is that on the right-hand side of our equation, the square root inverses the square, leaving us just the C. And the square root of 100 says, well, what times itself gives me 100? In this case, we know that is 10. So we know that C is equal to 10 inches. It's as simple as that. The next most common mistake here, other than labeling A, B, and C wrong, is to go ahead and stop when you get to C squared equals 100 and tell me that the length of this side is 100. Okay? That's another common mistake. Make sure that you actually solve for C by taking that square root. The last thing that we're going to do before we move on from any right triangle problem where we have used Pythagorean theorem is to double check what we know about the hypotenuse. We know the hypotenuse will always be the longest side. And so if it's ever not the longest side, based on our calculations, we know something is wrong. So here I see we calculated it out to be 10. that is bigger than 6 and bigger than 8, which means that this definitely could be the hypotenuse. Okay? The length is greatest of all sides. Questions, Triana? One more problem. First thing that we need to do with this particular problem is label A, B, and C. Before we can label A and B, we have to know where the right angle is. Somebody with a raised hand, describe to me which of these 3 angles is the right angle. RJ is pointing at the top one, the top-ish one. He's saying this is a right angle. If you are a little bit uncertain sometimes, I will tell you to go ahead and get out a handy-dandy angle checker. If you don't have one, I promise you, you do have one. It's a piece of paper. Piece of papers have 90-degree angles on their corners, and so all you have to do is line up your piece of paper with your angle that you are trying to figure out whether it is a right angle or not. And if it's a perfect fit, like those blocks that you did at the doctor's office when you were 3 years old, then it is a right angle. So, handy dandy angle checker. Get one. They're the best. All right. So if we know that that is our right angle, that means we know that the 2 sides that are given to us are A and B, and the unknown side is C. We know this is a right angle or a right triangle, so we will go A squared plus B squared equals C squared. We will plug in what we know. 5 squared plus 2 squared is equal to C squared. 25 plus 4 is equal to C squared. 25 plus 4 is 29. Is equal to C squared. So the length of this side is 29 inches. Thank you, Amanda. You should be outraged right now. No, Mr. Boots, there's no way that side is 29 inches. The square is 29. Oh, okay, okay, hold on. All right, so we need to finish solving for C. Our inverse operation to solve for C is what? C is squared, so we need the inverse of squaring, which is to take the square root. So that gets our C alone, and that tells us our answer is the square root of 29. I see the wheels churning. What times itself is 29? 5 times 5 is 25. 6 times 6 is 36. So there is no perfect square for this. So there are 2 ways we can leave our answer. I will expect you to leave your answer as both until you are given an answer choice. Your first answer is the square root of 29. C is equal to the square root of 29. But because most of us, that doesn't mean a whole lot, if I were to walk over to Paula and say, hey, I am the square root of 29 feet away from the door, she'd be like, what are you talking about? She could go through and go ahead and estimate that. We said that that's going to be somewhere going way back to Unit 2. That's between the square root of 25 and the square root of 36, which means it's between 5 and 6 inches. Between 5 and 6 inches. And we can box that in. Remember, the last thing that we always want to do before we walk away from a Pythagorean theorem problem is make sure that everything makes sense in terms of the lengths of our sides. The hypotenuse should be our longest side. And if the hypotenuse is bigger than 5, even if it's less than 6, that's still going to make it larger than our 2 legs that were 5 and 2. Okay? Questions?